Hi everyone, my name is Linlin. I'm from the latest lab inside Honeine University. Today I will present our work on matrix learning approach to graph edit costs for regression. Graph structure is a powerful tool to model a wide range of data, from molecule social network, handwriting to 3D point clouds and knowledge graphs. To measure the dissimilarity between graphs, a natural and widely used tool is the graph edit distance, namely the GED. To transform a graph to another, 6 fundamental operations are required. There are insertion, removal, and substitution between vectors and vertices and edges. The sequence of these operations composed of an edit path, denoted pi. Each edit operation is associated with an edit cost. The cost of the edit path is the sum of the costs of its associated operations. Then the GED between two graphs G1 and G2 is equal to the minimal costs of edit passes. Here we use the vector C to represent the edit cost of each edit operations, and the vector X to present the number of occurrence of each edit operations in an edit path. Then the GED can be rewritten as a multiplication of these two vectors. Edit costs have a significant influence on the performance of the GED, so it is important to find the best edit costs for a given task and dataset. There are several methods to do that. A traditional one is to set it manually. These costs are normally given by the domain experts with the domain knowledge implied. However, these costs are required a priori with the dataset, and they are hard to generalize to other datasets and tasks. Meanwhile, the information implied in the graph data may not be well explored. Another type of strategy is to learn the edit costs. There are several methods based on this strategy. However, they suffer from some shortcomings. For example, some have very high computational complexity, some restricted to strings and trees rather than generalized graphs, and some requires a ground truth mapping. With this knowledge, we propose a method to learn the edit cost by aligning GEDs and the distances between targets. Here, on the left side, is a space composed of graphs. The distance measure of this space is the graph edit distance. On the right side is a space of the targets associated with graphs. For example, these targets can be the value to predict for the regression tasks and the classes for the classification tasks. The distance between these targets are denoted by dy. To align these two spaces, we want the GED between two graphs as close as possible to the distance between the associated targets. Namely, let the GD1 equal to dy1, GD2 equal to dy2, and so on. Here we use the Euclidean distance for dy, that's one option. And this leads to a minimization of the sum of the differences between these two distances over all pairs of graphs. When the cost vector C is changed, the edit path between two graphs are also changed, as well as the corresponding vector X. So this minimization cannot be solved directly. We propose an alternated iterative optimization strategy to optimize C along with the axis. Each Each iteration consists of 2 steps. In step 1, we fix the edit costs and use the heuristics to compute graph edit distance and the corresponding edit passes and the vector x. The vectors x between all pairs of graphs compose of the matrix x. Then in the step 2, we fix the matrix x, and the minimization problem becomes a constrained linear optimization problem. We can use the classic solvers to solve this problem, and this procedure continues until the optimized costs are obtained. Next, we conduct experiments to test the performance of our methods. The dataset we use are molecules, namely the alkene and the cyclic. They are associated with a regression problem for their boiling points as targets. Alkene is unlabeled and a cyclic dataset has a symbolic label on nodes. We use a KNN regression to test our methods. 2 heuristics, bipartite and IPFP, are used to compute the GEDs. Here, the M represents the multi-stat counterparts of these heuristics, and M is equal to 30. A 2-layer cross-validation is used with 90% training datasets in the outer layer and 5-folder CV in the inner layer. The key of the KNN regression is optimized in inner CV over 5 candidates. The maximum number of iterations for our methods is fixed to 5. In this page, we show the results on each dataset in terms of RMSE for the 10 splits. 2 distances on the targets and are used, namely the Euclidean and Manhattan. The results of the fitted cost computed by our methods are shown in green bars. 2 other edit costs are compared with that. The random cost in the red bar and the expert costs in the blue bars. It can be seen that under all kinds of settings, our methods have a significant advantage over on RMSE compared to other methods. In this table, we show the value of the training errors and test errors. The best performance is marked with bold font, and we can see that the fitted costs outperforms all the other methods. Then we examine the optimized edit operations. Optimized edit costs. It can be seen from this table that the insertion and deletion costs are almost similar, which shows the symmetry of these operations. Meanwhile, the deletion and insertion costs are much bigger than substitution costs, which shows that the number of atoms is more important than the atom itself. In conclusion, in this work, we proposed a method that learns optimal graph edit costs for regression problems, where a matrix learning is used to align the GED space and the target space. An alternated optimization strategy is used to optimize the edit costs. The experiment shows that our method has a very promising results. The future work includes a comparison to the other methods that lures edit costs, a study of other criterion to lure the edit costs rather than the distance preserving criterion. A convergency proof for our methods is also interesting. We may also expand our methods to classification problems and non-constant costs, where the edit metrics may be optimized instead. And that's all. Thank you very much. Any questions?